Howdy class. Sent you an email this morning indicating that I'm going to be in Korea for the next 3 weeks basically. I'll be involved in an exercise there for the Navy, and what I'm trying to do today is to get all my lectures recorded in advance, so you'll have the next best thing to live lecture. You're going to have me by video in class for the next 3 weeks. Jose and Liz are going to be your contact people, so if you have any questions, ask them, and they should be, at least one of them should be in class each day, administering quizzes and handing out handouts and setting up the lectures for you to see in class. So let's go ahead and get started. Last time we were talking about semiconductors, just in terms of the basic materials and construction and that type of thing. Today we're going to start focusing on semiconductors with respect to transistors. Transistors were invented in 1956, and as we mentioned last time with semiconductors in general, they replaced vacuum tubes basically. Transistors perform a lot of functions that used to be used with vacuum tubes, and I gave you the illustration of my television set when I was a kid that had lots of vacuum tubes in it. Well, now we can make them quite small, quite flat, because they have transistors in them instead. Transistors have several advantages. One is they're much smaller, which is great because we like to make things in a smaller package and use less material. We also like the fact that they consume much less power than vacuum tubes did. They're also much more ruggedly constructed, which is great if you're using them like in an industrial environment or an agricultural environment where there may be a lot of rotating machinery around, or you may be driving over bumps in a field. They have to be able to withstand that shock and vibration, whereas vacuum tubes would not have done that. In that last 58 years or so, transistors have become the building blocks for all modern electronics and computers. So what are they basically? They are composed of 3 layers of material. We talked about N-type, P-type, and materials in semiconductors last time, and how that when you join them together at this interface between the 2 types, you get a zone of depletion, which serves as a barrier to electron flow. Well, in transistors, you're putting 3 parts of material together, and we'll call it a sandwich, and it can either be an NPN sandwich, N-type, P-type, N-type, or a PNP sandwich. And the 2 different types are used for different purposes. In each case, you've got 3 leads that are connected, one to each of the types of material. They are base, which is typically in the middle, and collector and emitter. And you'll see as we talk about FETs later that there are different names for these on an FET, which is a different type of transistor that we'll cover on the next couple of slides. So let's talk briefly about what an NPN type is, or why it's used differently than a PNP. If the base, which you see right here, these are the schematics for NPN and PNP transistors, and the base is shown in the middle here. If the base is at a higher voltage than the emitter, current will flow from the collector to the emitter. So imagine that from collector to emitter, you basically got a pipe going through here like this, and you want electrons to flow through there or not to flow through there, and you're going to valve that off by the voltage that you apply on this base right here, okay? A small amount, with typical transistors, a small amount of current will also flow from the base to the emitter. The voltage at the base controls the amount of current that flows through the transistor from the collector to the emitter. So again, the base voltage basically serves as a valve for current flow. Now in PNP, it works similarly, but in this case, if the base is at a lower voltage than the emitter, you get current flowing from the emitter to the collector. And a small amount of current also flows from the emitter to the base. Okay, so everything is basically going in reverse here. And once again, the voltage at the base controls the amount of current flow through the transistor from emitter to collector. You can note in both of these schematics, this last bullet says follow the arrow. Both of these schematics have an arrow that's a little strange looking, but it gives you a sense of the direction of the current flow. That's PNP. In this case, this little part of the diagram right here serves as an arrow to show you the direction of current flow there. So as I mentioned, there's one type of transistor called an FET. There's also one called a BJT. BJT stands for bipolar junction transistor, FET for field effect transistor. FETs are more popular because they don't consume as much power and run cooler. They're cheaper, and the main negative with them is that they're easily damaged by static electricity. And if any of you has ever popped open a computer box to work on it, such as adding memory or changing hard drive out or something like that, you should have known that you have to be careful about discharging static electricity inside the box onto the chips, because there are some of these numerous FETs inside there that can be damaged by static electricity. Between the two, BJT and FET, the basic operation is the same, but you'll note the construction's a little different, and I'll leave it to you to kind of look. You can see how they've got N-type, P-type material in different configurations. You'll also notice, hold on, let me put my glasses on here so I can read this. This is an oxidate that serves as an isolation barrier or insulator right here. And in the BJT, your collector contact is on the back of that. So you've got an insulator between your transistor, if you will, and your collector contact. Your base contact is here on the P-type material, and your emitter contact is here on the N-type material. So it goes N, P, N like this with an insulator in between. On the FET, you've got a metal part here connected to the P-type material, and you've got N-type materials here and here. Now, instead of base, emitter, collector, what we have is source, gate, and drain. But they basically mean the same thing, and we'll talk about that in a little bit more detail as we go further into looking at FETs. So, transistors can fulfill one or more functions in a circuit based on one operating characteristic. The bias voltage on the base, and you'll remember we talked about bias voltage last time. That just means it's a voltage that's applied to the semiconductor or the transistor. The bias voltage on the base and the small current between the base and emitter permit large current between the collector and emitter. So again, if you're talking about, in this case, current flowing from collector to emitter in this direction, think of this as a pipe, and the base is just a valve, but it's also allowing a little bit of flow to occur between the base and the emitter. The valve is adjusted by adjusting the voltage on the base here. The current between the collector and the emitter is proportional to the base to emitter current. Okay, so you adjust this voltage, which enables a little more current or a little less current to flow between base and emitter, and this current from collector to emitter will be proportional to that current from base to emitter. So transistors often are used to function as switches, and I mentioned this, I think, in the last lecture, talking about how semiconductors could be used as switches. Most sensors, processors, microcontrollers cannot provide enough power for actuators. So if we take a moment and think about an actuating device, and you'll remember from drawing your diagrams, your process control or block diagrams, that you've always got an actuator or control element in that block diagram. So what is that? Let's think about our peanut butter vat that we're trying to maintain at a certain temperature for a certain period of time to make sure that we're adequately cooking or processing the peanut butter. Now, to make that physical action occur, that heating of that vat of peanut butter, we're applying voltage or current to a heating element, and we have to have some type of relay or switch that allows that to occur. That's quite a bit of power that's going into that, and the control circuit, which is made up of these microcontrollers and sensors and so forth, does not have the power to make that occur. But we can use the transistors as switches where we apply a small amount of power, such as, let's go back to the last slide, we can apply that small amount of power to the base here, and we've got a separate power source that will provide the power from the collector to the emitter if we only adjust the small amount of voltage or current to the base. So that's basically how that works. Again, transistors allow a large amount of current to be controlled by a small change in voltage at the base. this allows switching a large current on and off, so we can go from 0 to full current. The grounds between the control circuit and the transistor must be common, otherwise we're not going to be able to control the flow as we desire. Using a transistor as a switch is the basis for digital electronics, including microcontrollers and digital computers. And that is the case because basically we're switching from no current or no voltage to full current or full voltage. And those are how we represent zeros and ones, okay, which is the basis of all electronics, electronic communications, digital communications, and that type of thing, bits. All right, we've learned what impedance is. It's a like resistance, right? Transistors have impedance. So if we remember the voltage divider equation, you can imagine the voltage divider circuit in your mind. The impedance of the subsequent stage in a series of electrical connections can alter the voltage or the current output from the initial signal. And we remember, if we want to represent the initial voltage well in a voltage divider, we need our voltmeter, if you will, impedance to be very high, okay, and that way we get close to an exact representation of the input voltage. Now, whether this signal, voltage or current, originates from a transducer or a microphone, or if you're an electric guitar player, you've got pickups on the electric guitar that do this, the loss of signal from having too low an impedance in subsequent stages can cause large errors in your output. So one great thing about transistors is that they have an extremely high input impedance, which you can imagine as your voltmeter impedance or resistance. That is extremely high in transistors, and they have extremely low output impedance. And this basically means that when you put them in the circuit, you can assure that the impedance guidelines for that circuit are met, and you can do a very good job of representing the input signal to that transistor. So we talked a little bit about switches as a use for transistors. What about amplifiers? Well, the current flowing in the collector, remember we talked about flow between collector and emitter, the current flowing in the collector is proportional to the current flowing in the base. That is up to a saturation level or saturation value. That's a maximum that it can amplify. This is a property of a particular transistor and circuit. So the ratio of the collector current to the base current is the amplification. So for example, if we have a base current of 1 milliamp, imagine what the current could be at max amplification in the collector if we had a max amplification value of 100. Okay, take 1 milliamp, multiply that by 100, and what do you get? You get 100 milliamps, right? Or 0.1 amps would be what you could move through the collector based on what the base current was. By limiting the voltage at the base, we can limit the current through the circuit. So we're able to do this by changing voltages at the base very readily. This all works very well. Okay, so let's talk about the BJT, the bipolar junction transistor. It has 3 terminals. It's basically the one that we've been talking about, where it's got base, collector, and emitter. And it can be either of NPN or PNP construction, and you'll see with the PNP you get your arrow for current flow pointing that way, and with your NPN your arrow for current flow pointing that way. Now, note in the diagram that I just showed you that the direction of the emitter arrow is defined by the type of the transistor, and that's why we use PNP and NPN separately. The arrow always points to the N-type material. Let's just go back and look at that again. So this is a PNP, so the N-type material is in the middle where the base is, and the arrow is pointing towards the N. On the NPN type, you've got N here and N-type here, and the arrow is pointing towards the N-type here. So it always points towards the N-type semiconductor material. Biasing and power supply polarity is positive for NPN and negative for PNP transistors. Okay, you remember forward and reverse bias from the last lecture. It's positive for NPN, negative for PNP. Thus, for an NPN transistor, the base voltage is greater than the emitter voltage. Okay, so that's a positive or forward bias. The collector voltage is greater than the emitter voltage. Okay. For a PNP transistor, the emitter voltage is greater than the base and collector voltages, and that is a reverse bias. Okay. Circuit designers often use both NPN and PNP transistors to take advantage of voltage changes in the circuit depending on what they desire that circuit to do. So both types are used. Now, we talked also about the breakdown voltage in semiconductors last time, and basically that was something that we tried to avoid except in Zener diodes. The breakdown voltage is a design limitation with all semiconductors. Breakdown voltages must be accounted for each pair of terminals. Okay, so we don't want to exceed the voltage and destroy the transistor. However, collector emitter voltage with an open base is usually of most concern and defines the maximum circuit voltage. Also, as with all semiconductors, there are undesirable leakage currents, and we showed you I showed you diagrams of that last time, how we get leakage current. This is notably collector junction leakage and emitter junction leakage. So there is some leakage at those junctions, and that's just unavoidable. We try to minimize it, but it is unavoidable. All right, so we're just talking about BJTs. Now let's talk about FETs. That's field effect transistors. There are two different types we'll talk about, the junction FET and the metal oxide semiconductor FET or MOSFET, JFET, MOSFET. Both are voltage control devices. That is, a small change in the input voltage causes a large change in the output current. Sounds like a BJT, right? Pretty much does the same thing there. The FET or FET operation involves an electric field that controls the current through the device. In contrast, a BJT employs a small input current to control a large output current. This is an important point here. Okay, a BJT has a small input current that goes from the base to the emitter, right? The FET does not. It uses an electric field, so you're actually not using current to regulate the current through the device. The source, drain, and gate terminals of the FET are analogous to the emitter, collector, and base of the BJT, okay, respectively. So the emitter is like the source, the collector is like the drain, and the base is like the gate. N-channel and P-channel refer to the polarity of the FET. N-channel FETs exhibit conduction by electrons, whereas P-channel FETs exhibit conduction by holes. So what are FETs good for? Well, they're suitable for the following. Very high input impedance, which means no current at the gate, which is good. We don't waste any energy there. We can regulate that strictly by using a voltage and no current. They also act very well as bidirectional analog switches. Simple two-terminal current source and a voltage-controlled resistance. So anytime that you're desiring one of these in a circuit, an FET-type transistor is a very good choice. So there are variables that you have to think about here, and so we've got N-channel or P-channel types, right? We've got semiconductor junction or oxide type insulators, and we've got the way that they're doped in terms of enhancement or depletion. So there are three different variables. Each one has two possibilities. That gives us 2 to the third is, 8 theoretical combinations, okay? So you could have an FET that was N-channel, oxide insulator, depletion channel doping, or any other combination of those. But basically only 4 of these combinations are a practical concern. In the JFET, we're going to have depletion mode in both of those, but we can have either N-channel or P-channel. In the MOSFET, we can have only enhancement mode, and again, we'll have N-channel or P-channel. So basically, the idea is here, in both JFETs and MOSFETs, you can have N-channel or P-channel type FETs. N-channel depletion mode MOSFETs exist, but they're used primarily for radio frequency operations, something we won't deal with. We're only going to consider enhancement mode MOSFETs. Enhancement mode FETs do not conduct between source and drain unless a voltage is applied to the gate. Okay, well, let's think about that just for a moment. That means that they have a current flow of 0. Okay, so once you apply voltage to the gate, you get flow. So that's either yes flow, no flow, 0, 1. Okay, depletion mode FETs conduct between the source and drain until they are turned off by a signal at the gate. So they operate just the opposite. Give you the same effect. You can either have flow or not flow, but it's the default state with the depletion mode FET is that they are conducting, whereas with an enhancement mode FET, they are not conducting in default mode. All JFETs are depletion mode devices. So here's a schematic for a MOSFET, and you can see that the insulating layer, the gap between these leads and the gate, is shown in the diagram, a little bit of a gap in there. You can also see that in a P-channel type, you've got your arrow pointing in this direction, and in the N-channel type, you've got your arrow pointing in this direction. Okay, here's a schematic of the construction of P-channel and N-channel MOSFETs. You've got your gate here, you've got an insulator here on your N-type material, your source, and your drain. On the N-channel, you've got the same thing basically, but it's NPN instead of PNP. Okay, so let's talk about an N-channel enhancement mode MOSFET. It's analogous to an NPN BJT, and you can go back, once you get these notes, you can go back and look at the NPN BJT and compare it to the enhancement mode MOSFET and see how they're similar. In normal operation, the drain is more positive than the source. Okay, that's in terms of voltage. No current flows from drain to source unless the gate is brought more positive than the source, meaning the voltage on the gate is increased so that it's higher than the source voltage. What this means is it's forward biased. Okay. Once the gate is forward biased, current will flow from the drain to the source. A larger gate to source bias produces a larger drain to source current, so you can actually regulate the level of the current that you're getting by changing that voltage. The difference with NPN BJT type transistors occurs in the relationship between the gate voltage and the drain current, and in the fact that there is no gate current. Okay, so that's a biggie. There is no gate current on a MOSFET. On the BJT, there is current that flows between base and emitter. Because of the insulating layer, the MOSFET has very high input impedance, higher than the JFET and much, much higher than the BJT. So if you're really desiring to have that extremely high impedance to do a great job of reproducing your input signal, then a MOSFET works very well. This allows the MOSFET to control current with gate voltage that draws no current. This makes the MOSFET ideal to interface with microcontrollers and microprocessors, devices that simply cannot supply a lot of current. So this is these are the schematic symbols for the P-channel and N-channel FETs. Here you've got not an insulating layer. It's a different material on the back here. You've got drain, gate, source, much in the same way as you did with a MOSFET. You'll notice also that on the P-channel your arrow is pointing towards the gate, and in the N-channel it's pointing away from the gate. So the JFET only operates in depletion mode, as we discussed earlier. That is, it conducts all the time unless you apply a voltage to it to turn to the gate to turn it off. So a map of input-output voltage for FETs, and this is the source or emitter is grounded. A map of input-output voltage for the FETs is shown below. So let's look at this just for a moment. Here, on this axis here, this shows that you've got So this shows that when the drain or collector voltage is high and the gate or base voltage is low, you've got an N-channel depletion MOSFET or an N-channel JFET. When the drain or collector voltage is high and the gate or base voltage is high, you've got an N-channel enhancement MOSFET or an NPN BJT. When the drain or collector voltage is low and the gate or base voltage is high, you get a P-channel JFET. And when the drain or collector voltage is low and the gate or base voltage is low, you get a P-channel enhancement MOSFET or a PNP BJT. So you can think of all the times when you would want current to flow one direction or the other, and this diagram here shows you what options you have for the various types of transistors. So with the source grounded, a FET is turned on by bringing the gate voltage near to active drain supply voltage. So here are some, I'm going to go through about 3 different semiconductor devices that are based on transistors. This one is called a silicon controlled rectifier, or SCR. It's basically a conventional diode that is controlled by a gate signal. You remember we covered diodes last time. It's either an N and P junction or a P-N junction, except in this case there you've got a gate on it like you have with a transistor. So it's a conventional diode controlled by a gate signal, and this is a schematic representation. You've also got triacs, which are basically a 3-terminal semiconductor. You see 1, 2, 3 terminals for controlling current in either direction. So a triac you can use to force current to go one way and then the other way. That's the schematic symbol below. It looks like 2 silicon controlled rectifiers in parallel, one this way, one that way. And the main or power terminals are designated as T1 and T2. When the voltage here on T2 is positive relative to T1, and you have a positive gate voltage, then the SCR pointing to the left, this one, conducts. Okay, so you've actually got like 2 pipes, and you're regulating which one of these conducts. When the voltage is reversed and negative voltage is applied to the gate, and you've got higher voltage on T1 than T2, then this SCR conducts, so the other pipe has current flowing, in this case to the right. As with the silicon controlled rectifier, minimum holding current must be maintained in order to keep a triac conducting. So you have to have some level of current applied. Some of the applications of these are in phase control, inverter design, AC switching, relay replacement. Okay, you're trying to put something in instead of a relay. These can work because they will allow current to flow in one direction and then the other. Good job of switching. Another device is called a diac, and a diac is a bidirectional trigger diode. So again, it is a diode designed specifically to trigger a triac or an SCR. Triacs and SCRs were on the last couple of slides. So how do we trigger those when they're acting as switches? A diac does not conduct except for a small leakage current until the breakover voltage is reached. At that point, the diac goes into avalanche conduction, and it exhibits negative resistance characteristics, and voltage drop across the diac snaps back, typically about 5 volts, creating a breakover current sufficient to trigger a diac or SCR. So if you think about this, it's sort of like a hand-turn switch where you're actually making contact and getting a rapid increase in conduction. But this is all happening electronically with diac. That schematic at the bottom is representative of the diac. And that is it for today's lecture. I'm going to try to get the camera back on myself. It may take just a moment. So the homeworks that you have are going to focus mainly on the prior material that I've covered. The things that I'm covering right now with respect to semiconductors and transistors are mainly for knowledge. We may get into use of BJTs, FETs, that type of thing in the lab if we've got time. But this is mainly for your general knowledge of electronics, and we're not going to be doing calculations with MOSFETs and JFETs and so forth. But the homework will continue on the same vein that you've been on. So look forward to being back with you in a couple of weeks, and please keep up the good work. All right.